Hello and welcome to the first video about the wave behaviour of light. In this video we will do a recap of some stage 1 content just about waves and their features, and then we'll quickly revisit some electricity and magnetism concepts, and then we'll look at the features of electromagnetic waves, which is the type of wave that light is. Apologies if you can hear like a staticky sound in the background. Maybe you can, maybe you can't, I'm not sure. But it is raining outside, so I'm not sure if the rain is getting picked up by the microphone. So this page here is just a recap of some stage 1 concepts. So waves are periodic disturbances due to continuous oscillations that transfer energy between a source and a distant point without the transfer of mass. So a type of wave can be mechanical waves, and these need to propagate in a medium. So for example, air, earth or water. Mechanical waves include waves like sound, or like waves at the beach even. With sound waves, they're like the particles in the air are vibrating, and those vibrations are getting transferred along to someone's ear. Progressive waves propagate outwards from a source, and both transverse and longitudinal waves are progressive. So the top spring here is representative of a longitudinal wave. This is a type of wave that sound waves are, where the direction of vibration of like the particles or the whatever is oscillating in the wave is parallel with the direction of the wave's propagation, so the direction that the wave is travelling in. Transverse waves are represented by the slinky, the second slinky, and in transverse waves, the particles or the things that are vibrating or oscillating are moving perpendicularly to the direction of travel. So the direction of travel of this wave is still going towards the ball from the hand, but the particles of the slinky are moving up and down. With light, the direction of the components that are oscillating move perpendicularly to the direction of the light's travel. So light is a transverse wave. We'll see in a moment that light is made up of two waves that oscillate perpendicularly to each other, but both of those oscillate perpendicularly to the direction of light's travel. Light doesn't need to travel in a medium, so light can travel in a vacuum, so there doesn't need to be any particles in order for light to propagate. So it's not a mechanical wave. So this slide in particular is just a recap of transverse waves, which we've already mentioned. The reason I wanted to have a look in particular at this slide is just for some terminology. So a crest is the peak of a wave, in the positive direction. A trough is the peak of the wave in the negative direction. So the lowest point of the wave, or the maximum negative displacement, contrasting with the crest, which is the maximum positive displacement. The amplitude is the displacement from zero, so the 0 point. So the lines that I've just drawn from 0 to the peak maximum displacement, which is the crest, and the peak negative displacement, which is the trough, those distances are the amplitude. I'm going to get a different colour. The wavelength is the distance over which the shape repeats. So the wavelength could be from here to here. It could also be from here I think I've gone a little bit over there, to here. So basically just to the same point on the wave as it's repeating again. It could be from crest to crest, it can be from trough to trough, it can be from a 0 point that's about to move in the same direction to the next 0 point that's going to move in the same direction. So you wouldn't have a wavelength from here to here, even though they're both, the wave's displacement is both at 0 for these points. It would only be half a wavelength because the direction that the wave is going to move from here is up, but from here, the direction that the wave is going to move is down. So that's not a wavelength. The period is the time over which the wavelength is repeated. Now this graph doesn't really show us the period because it's a displacement position graph. So we'll move on to the next page that does have the period represented here on a displacement time graph. So the period, as you can see, is from the same point on a wave to the next same point, but it's measured in time. So from the time it takes to get from a crest to a crest, the time it takes to get from a trough to a trough, or it could be the time it takes to get from the same point on a wave to its repeating point. So essentially the period is the time over which a wavelength is repeated, or the time it takes for a wavelength to occur. And it's measured in seconds. I think I mentioned that already. The frequency is a number of repeating cycles of a wave per given time interval. So frequency and period are inversely proportional to each other. So frequency is how many periods occur in 1 second. So the units for this are hertz or per seconds, which is just s to the negative 1. If you've been given the frequency and you need to work out the period, you just do the inverse of the rule, or just rearrange the rule rather. So it'll be 1 divided by frequency. Hopefully you can see that's just a rearrangement of this rule here. If you need to find the frequency and you've only been given the period, then you just divide 1 by the period, and that'll tell you how many times the period occurs in 1 second, and therefore how many wavelengths are occurring each second. Something else worth mentioning is just the wave rule or wave formula. This is just wave speed, which is represented by a v for velocity, is equal to the frequency of the wave multiplied by the wavelength. If you're multiplying frequency, which is measured in per seconds or in hertz, by the wavelength, which is just measured in meters, you're going to end up with meters per second as your units, and obviously that's the unit for speed. This formula can be rearranged. So for example, if you need to be able to find the frequency of a wave and you've only been given the velocity and the wavelength, you can just rearrange this formula so that frequency is equal to the wave speed divided by lambda, which is the wavelength. Then you just plug your values in and you'll be able to go from there. This slide is just a recap from electricity and magnetism last term. So you just need to remember that a change in magnetic flux, which could be due to a change in magnetic field, produces a potential difference, so a voltage or an EMF, and an electric field is induced. This causes a current to flow in a conductor, but even if a conductor is not present, the induced electric field is still present. So that's represented by these drawings here. So in this first one here, we've got a conducting loop situated in a magnetic field that has just changed. So there's a change in magnetic flux. The current or the electric field has been induced, and therefore a current is flowing in the conductor. If this ring or this conducting loop didn't actually happen to be there, the electric field would still be produced. There would just be no current induced because there'd be no conductor for the current to be induced in. The other thing to remember is that a change in electric field produces a magnetic field. So therefore changing an electric field or a magnetic field will produce a field of the other kind. So changing an electric field will produce a magnetic field, changing a magnetic field will produce an electric field. And that is how electromagnetic waves propagate. So because a change in electric field or a change in magnetic field produces a field of the other kind, this means that both fields can propagate through space via this phenomenon. So in this little diagram here, we've got the electric field which is propagating or oscillating vertically. The magnetic field oscillates horizontally, and then the direction is in the third plane. So for example, if you had X here, Y here, and Z here, then the electric field would be propagating or oscillating in the X plane, the magnetic field would be propagating in the Y plane, and the electromagnetic wave itself would be propagating in the direction of Z, so in the Z plane. So it's important to remember that electromagnetic waves are transverse and mutually perpendicular. So that means that the electric fields and the magnetic fields oscillate perpendicularly to the direction of the wave propagation. So that corresponds with transverse. I'll just highlight that. So to the direction of wave propagation. And they're also mutually perpendicular, so that means that they're oscillating at 90 degrees to each other. I've kind of mixed that sentence around the wrong way there to correspond with the order of the first dot point, but that's what they mean. So transverse means oscillating perpendicularly or 90 degrees to the direction of the wave propagation. Mutually perpendicular means that the electric field and the magnetic field are oscillating at 90 degrees to each other. Electromagnetic waves, I mentioned before, don't require a medium to travel in, so that means that they can propagate in a vacuum or they can travel in a vacuum. This contrasts with mechanical waves, so for example sound waves which need a medium to travel in because sound waves is the vibration of particles. If you create a vacuum, or if you literally suck out all of the particles from a space, then a sound wave won't travel. You won't be able to hear any sound. There's some videos on YouTube which I might link to where there's like a phone or something playing a song in a vacuum. The vacuum takes all the particles out of the particular space, and then you can no longer hear the song playing anymore, or a bell ringing or whatever is in the vacuum. Electromagnetic waves propagate through space indefinitely unless they're absorbed by something, and they're produced by oscillating charges. They also carry energy between locations. With the oscillating charges, we'll delve into that a little bit further in the next video where we look at radio waves. The last thing to remember is that electromagnetic waves have a frequency equal to the frequency of production, and this will make a little bit more sense later on as well. But for example, if waves are produced by an alternating current, the frequency of that oscillating current will also be the frequency of the wave. So whatever the hertz are for the oscillating current will be the hertz for the wave. These are just some GIFs, some graphics of electromagnetic waves. So in the first one you can see the oscillating charge moving back and forth, and then the electric field is produced in the same direction as the charge is oscillating. The magnetic field because it is mutually perpendicular, is produced at 90 degrees to that electric field, and then the wave itself is propagating in perpendicularly to both of those electric fields and magnetic fields. So in 3D space, obviously there's three different directions that you can have, or three different planes that you can have. The bottom GIF is just another representation of an electromagnetic wave. So the red usually represents electric field, so that's in the vertical plane, and the magnetic field is in the horizontal plane.